Alright, what's up everyone? Welcome back to Structure Free Learning. And in this video, we continue our structural analysis slash static sequence. And in particular, we're going to talk about or do an example problem calculating reactions of an angled beam here, AB, roller supported at A, pin supported at B, and we're given this trapezoidal loading that's perpendicular to the beam. And what we want to do is calculate the external support reactions. Our basic approach, just like with any problem where we're trying to determine just the reactions, are to draw that free body diagram, check determinacy, and apply the equilibrium equations. So here in this case, we're going to draw a free body diagram, and in most cases when you draw that free body diagram, you want to use the drawing that's given to you, especially in an exam situation. You don't want to waste time redrawing everything nicely. And so here I want to draw this AY, and then I have the horizontal and vertical reactions at the pin support at B, so I'll call that BY, and this BX. So with that, now I want to check my determinacy, and what we want to look at here, in this case, because we have only one beam component or one member, the number of reactions is that we have, or the number of unknowns really, this is kind of the same as the number of unknowns, that's equal to 3 for the support reactions. And then the number of equilibrium equations that I have available to me are 3. I have the sum of the forces in the X, in the Y, and some of the moments about a point, and therefore this is statically determinate. If it were statically indeterminate, we would have to use an additional or another technique to determine all the support reactions. This is determinate, so it's going to be a pretty straightforward problem. We can apply the equilibrium equations to solve for these reactions. The only challenge maybe is this angled beam and the way that the loading is. It doesn't have to be complicated if you make good drawings for this. So one of the first things I want to do is kind of resolve this trapezoidal loading. And I could try to figure out the centroid location for the resultant of this trapezoidal load, but I think an easier way is to apply the principle of superposition and separate the two loads. And so here I'm going to break this up into a linearly distributed part right here, which is going to be this purple shaded region. And here, if this is 0 for that purple shaded region, this portion right here is going to be 2 kip per foot. This uniformly distributed part, which I'll shade this way in green, and this is also 2 kip per foot going downwards. I've broken this up into 2 distributed loads, and now I'm going to go ahead and resolve kind of the locations of the resultants. Here, this is a triangle, so the centroid of the triangle is 1/3 from the fat side. And so right about here, I'm going to have the resultant of the linearly distributed load, which is the area of a triangle, and that is simply 1/2 the base, which I'll call 10 feet, times the height, which is 2 kip per foot, and that tells me this is going to be 10 kips. The location of this resultant is, again, 1/3 from the fat side. The green, or the uniformly distributed loading, is at the midspan of the beam. It's right in the middle, so this is that location right here. And the intensity, or the magnitude of this distributed load, is the area here, which is 2 kip per foot times 10 feet, which makes that 20 kips. And the location of this is just right at midspan, so this is 5 feet from that support. So now I'm ready to apply the equilibrium equations, but before I do that, let's make sure that we understand the geometry, or at least that we can break down the horizontal and vertical components of these forces. And one thing I like to do when I have this situation of angled forces and an angled beam is I want to kind of zoom in, if you will, on one of these. So I'm going to redraw. Here is that beam segment, and then perpendicular to that I have a force at one of these resultants. So I'm just going to draw a red line for that right here. And this is how I would resolve the geometry. This I know is 30 degrees, and one of the first things I like to do is draw a vertical and horizontal lines at the point of intersection. I know from here, parallel lines and all that business, 30 degrees here, I know that this these two lines right here make 90 degrees, which makes this 60. And then here would be 30, and here would be 60 again. Once I zoom in, I draw this out, I can work out all the other angles around this force. And that way I know that the horizontal component of this is either sine of 30 or cosine of 60. And the vertical component of this is either cosine of 30 or sine of 60. Alright, so now, hopefully if you have that understanding, then now we're ready to just go ahead and straight up apply the equilibrium equation. If I look at some of the moments first about a point, let me take moments about point B. And I like to take moments about point B because I have two unknowns here and I can solve for AY directly. I will have negative AY times the perpendicular distance. This distance here is 10 feet cosine of 30 degrees. So minus AY times 10 foot times cosine of 30 degrees plus 10 kips. And the distance is 2/3 of 10 feet. So that's going to be 20 feet over 3. Plus the 20 kips caused by the uniformly distributed part times the perpendicular distance to point B, which is 5 feet, equal to 0. And when I go ahead and I solve or I plug and chug, I can, cancel out some tens and feet here. And now when I go ahead and I solve for AY directly, I would get AY is equal to 16.67 kips divided by cosine of 30 degrees, which is equal to a positive 19.25 kips. And that positive result, using a global equilibrium equation, tells me that the direction I drew AY is correct. So this AY is 19.25 kips pointing upwards. Now I can apply some of the forces in the horizontal. I'm going to be able to solve for BX directly, and that's going to be BX plus the horizontal component of this 10 kips. So that's going to be plus 10 kips times the cosine of 60 degrees plus 20 kips times the cosine of 60 degrees equal to 0. This will just tell me that BX is equal to negative 15 kips. This negative 15 just indicates that, this BX is in the opposite sense. Not necessarily incorrect, but opposite sense. So this is the same as 15 kips to the left. And last but not least, some of the forces in the vertical. And here I would say that AY plus BY minus 10 kips sine of 60 minus 20 kips sine of 60 is equal to 0. And again, I would substitute for AY here. AY is 19.25 kips. And now if I solve for BY, I would get that BY is equal to 6.73 kips, with a positive result which indicates that BY is equal to 6.73 kips pointing upwards. And these are my reactions. Alright, hopefully that was simple and relatively straightforward. If you have any questions, let me know, and take it easy. See ya.